Hello, ladies and gentlemen. This is take two because with my live audience, I accidentally left the microphone muted for the recording, and so we're going to do this again. So, the first thing I want to say is that if you participated in the community event yesterday, first of all, thank you. It was fun. Secondly, if you did not type your name in the chat, you need to email me so I can ensure that you get the points for the community event. Thanks. So, I'm going to be talking about Professor Chandler information, and then from that, hopefully you feel prepared for the exam, and you can also find out what you got wrong on the quiz. Also, it is worth noting that all of the quiz keys have been posted, so you should be able to access those at this point. If you can't, let us know. So, I'm going to begin by talking about the stretch reflex. So, the stretch reflex is the easiest of the two reflexes that we are talking about in this class, and essentially what its goal is that it wants to keep the limb in the same position if there's all of a sudden an unexpected load increase or something that is moving your arm unexpectedly. So the receptor organ is the muscle spindle, which we've talked about. The muscle spindle, when stretched, initiates an action potential that goes down the 1A fiber, which is the name of the sensory axon for this reflex. And that 1A fiber monosynaptically connects to a motor neuron, which comes back and tells that same muscle to contract a little more to make up for that stretch. Okay, so it's correcting the length, the lengthening. Okay, it's extremely fast because it is monosynaptic, and it uses excitatory glutamate. So what does it look like? Well, I'm so glad you asked. First of all, you have the muscle spindle here. When that is stretched, maybe by an increased load on the hand, it will lengthen this muscle and thereby lengthening this muscle spindle. Next, that action potential is initiated on the axon, and it goes through the 1A axon, past the cell body of the 1A axon, which is in the dorsal root ganglion here, and it comes in, where it splits in two. It is excitatory glutamate, like I just mentioned, so that's what it releases, and so at both of these synapses, it's going to be releasing an excitatory neurotransmitter. So let's focus on this side first. So what happens is we come in, we have one synapse, and it activates this motor neuron, which comes back and tells that exact same muscle to contract. Okay, it says, you are being pulled, you need to do more work to make up for that. On the other hand, this side is going to be inhibiting the antagonist, the opposite side, to make it easier for this guy to do his job. Okay. Now, it's impossible for this to directly connect here because we already know this one is a positive sign. So it would be activating if this one directly connected to here. And then this would be tightening as well as this. So that's not what we want. So we have to have an inhibitory interneuron there. Inhibitory in that it releases a negative symbol or an inhibitory motor neurotransmitter to inhibit this motor neuron and thereby discourage the triceps or the antagonist muscle to contract. An interneuron, by definition, is a neuron that starts and ends within the spinal cord. Okay? So, stretch reflexes do three things. First of all, you have a monosynaptic initiation of the agonist. Okay, so to go back, that is this monosynaptic initiation of the agonist right here. Okay, we also have the disynaptic inhibition of the antagonist. So that is this. So it takes two synapses to get to this one. Okay, but the third thing is we tell the brain what happened. That is not shown here, but what happens is you go off into the white matter and then you shoot up to the brain and you say, hey, this is what we're doing and this is what has happened. Okay, and that is how proprioception is done. It's through this third step. Okay. Okay, so the next thing we want to do is discuss the illusion. Okay, and so what I'm going to do is I'm going to try to walk you through every step of this by showing you what happened and then explain each step along the way. Okay, so in order to do that, you are going to have to watch very carefully. Okay, so here's how it works. First of all, you need a vibrator, or in this case, a banana stepping in as a vibrator. Okay, so essentially what happened was Dr. Chandler initially called a student up, and that student was blindfolded so that they could not use visual cues to change whatever they were maybe going to do. So initially what we did was Dr. Chandler just had the blindfolded student, he moved the hand like this, and then he said, can you match it? So the student moved here or here or whatever, indicating that they were about equal. So you want to make sure that the student wouldn't just like do this and show that they don't have proprioception. So it was essentially a control measure. If the student had not been able to match that, we would have just sent them to the neurologist to be checked and then got a new student to kind of do the same thing, okay? So next, what we did was Dr. Chandler had the student put both elbows on the table, and then he took the vibrator and applied it directly to the tendon in the bicep right here, okay? Now, what happens is those spindles that I just talked about in the stretch reflex, they're really susceptible to vibration. And so what you can do is you can essentially fake them out. You can say, hey, we're being stretched even when you're not. So you're indicating maybe an increased load or you've been pushed down, okay? Even though that is not the case. So we falsely initiated this. And so this signal was sent to the brain as part of that third step that I was just saying. Hey, we're going this way. Even though in reality, the stretch reflex had been activated that had pulled it up. So if you remember, what actually happened was he applied the vibrator and the arm came up because of the stretch reflex. This was initiated and this was inhibited. So boom. Now, what you need to know to understand this is that there are 4 receptors in the arm. There's the stretch receptor here that I just described, the spindle stretch receptor right here in the other muscle, the antagonistic muscle, and then you also have in the joint capsule, you have essentially the same thing, okay? So you have a stretch receptor or an angle receptor both on this side and this side of the elbow joint. So what happened to the brain was it got a signal from right here in this arm saying, we're going down, we are being stretched. However, the arm came this way, it did not get stretched. And so the brain is getting messages from here, here, and then no message from the joint capsule there because it's not being stretched. And so the brain says, one person says you're lying, or I'm sorry, one person isn't saying anything, and they should be if you're telling the truth, and both of these say you are lying. So I don't think I believe you. And so it says that this one is lying because the others all disagree. And so the student correctly pulled the arm up to match up, even though this one, the stretch receptor in the bicep, had been lying about it and saying that it was going down. Okay. Now, second step. Dr. Chandler again took the vibrator, applied it to the same tendon where it sent the same signal. So it said, I am being stretched and I'm being lengthened. I'm going this way. Okay. Now, what Dr. Chandler did was when the stretch reflex happened that would normally pull the arm like this, he held it in place so that the arm did not move. It stayed still. Okay. It didn't move in any direction, even though this muscle probably slightly contracted to kind of try to compensate. So he held it still. Now, what happens when you hold that still? Well, this muscle is no longer lengthened because nothing is changing. This joint capsule doesn't send any signal because it's also not being changed. And this one is also silent, okay, which is a little suspicious, but the brain only has this one thing, and none of these guys voted. So it only thinks that this is happening. So even though her arm stayed here, she went like this down to the table and thought her arm was there. Okay? This is why you vote. Okay? Because if this guy votes wrong, we need these other voters to drown them out. If you stay home, this person wins. Thank you. That has been my shameless plug of the day. Okay, so let's go back to the slides and see what we can do for these next few things, okay? So now that we've discussed this, let's go to the withdrawal reflex, okay? So you're going to need to be able to draw this withdrawal reflex, just like you're going to need to be able to draw the stretch reflex. They are different, and you need to try to mentally keep them separate. Okay? Now, what I'm going to try to do is explain to you how to do this in the most efficient way possible for memory. Okay? So, what you need to do is you need to try to diagram it, but you need to start at the bottom and work your way up. So what I'm going to do now is I'm going to draw this for you and then hope that it makes sense, okay? So I am going to start by making a rough, very rough shape of a spinal column, and then I will draw this in. So you can imagine that kind of the rough butterfly shape for the gray matter is here. And then here is the midline, right? So I have this coming in, and this would be the dorsal root ganglion that I just drew right here. And then you have the opposite side doing essentially the same thing. And then these are going to be where the motor neurons are leaving via the afferent pathway. So what you do is, we know that sensory information is coming in, right? Draw it to there and then stop. Please do not do anything else. It will make your life challenging. Okay? So what you need to do is you need to go there and then just stop. Okay? And then we start from the bottom and work our way up. Makes your life so much easier. So, we're assuming that the injury is happening on this side. So this is the ipsilateral, and this would be the contralateral side. Okay. So first of all, to start, you just write Fifi. F E F E. That stands for flexion and extension of that leg. Okay. So while I'm not going to be showing the muscles, that would be the signal sent to the muscles via these motor neurons. So now what I need to know is, what do I want each of these to do? Do I want them to flex or extend? So if this is the hurt side, the injured side, I stepped on a tack on this side, then I am going to want to pull the injured leg up and away. So I'm going to flex the injured side, okay? Decrease the joint angle at the knee. And I'm going to inhibit extension so that this works more effectively. On the other side, I need to now stand on that leg. So at the knee joint, I want the extension to be initiated and held strongly, and I want to inhibit flexion. Okay? So, let me draw my 4 motor neurons coming in very roughly. And obviously, in lamina 9 right here, approximately, is where the heads of these motor neurons would reside. The cell bodies of them. Okay? So, next what you do is you do something actually that's pretty easy. You draw an interneuron on every single one of these. Okay? Just a small interneuron on all 4 of these. Now, this is where these symbols come into play. So down here at this synapse, what do I want? Do I want a positive or a negative? Do I want excitatory or inhibitory? Well, you just match what we did here. So for the flexion, no, I do not want flexion. So I'm going to inhibit at that joint, or at that synapse rather. And I'm going to excite at this one. And then conversely, on this side, I'm going to excite at this synapse. And I'm going to inhibit here. So what that means is this interneuron is an inhibitory interneuron, and this one is an excitatory interneuron. It's releasing excitatory neurotransmitter, and this is releasing inhibitory. Okay? So now that I've done this, it gets progressively easier as you go, actually. So the next step is to draw an interneuron that actually merges with itself here and then crosses the midline. Okay. Now, after we have done this initial row of minuses and positives, or excitatory and inhibitory signs, everything else is just excitatory. It's quite straightforward. So everything else that you're going to draw throughout this entire drawing is excitatory. Now, we have reached the phase where we can come up here and bring this sensory neuron in. And what actually happens is it splits into thirds. You get that, and then you get this, and you get this. Okay? And all of these are excitatory. So, you may have the question, why do I need to have an interneuron at this junction? I could just have this come directly down to this motor neuron because it's just a plus and a plus. It doesn't make sense. Why? I could be much faster. But it's not just about speed. It's also about how strongly you contract. So if you have a very hot cup of coffee in your hand, that hurts. And you're going to probably withdraw from it if you go to grab it. However, that's going to be a different response than if you touch literally molten lava. Okay? And if you had the same response for that, you would throw your coffee quite frequently. So the reason you would have this is for modulation. Okay, there are two reasons to have interneurons. One, if you need to switch signs, and two, because you can respond in varying amounts. So you might not react quite as strongly to hot coffee as you would molten lava. Okay, I hope this makes sense. Let me know if you have questions. Okay. So, next we're going to talk about the CPG, also known as the central pattern generator. So, there are three things shown here. So, there's this case study, and this case study, essentially, of cats. And then part D is presenting a potential mechanism that would explain the results found here. So what I'm going to do is I'm going to try to walk through each one of these individually, and then I will actually talk about this in quite a bit of detail on the next slide. So we start with this one. What happened here was we took a cat and they paralyzed it. Paralysis would affect the acetylcholine in between the motor neuron going to the muscle. It does not affect any of the other things in the nervous system. So you still have calcium coming in at that axon terminal near the muscle, and initiating vesicle release and everything. So you can measure those things in terms of the thought question that you might be thinking of at this moment. But anyway, so you cannot contract the muscles because you're paralyzed, because the acetylcholine is being inhibited, essentially, or taken out by the paralysis drug. So you likely are not sending a lot of sensory information back because you're not moving. So you're not receiving any new sensation for the most part. So then they looked and they said, well, I'm not receiving a lot of sensation, but we still see this weird pattern of action potential generation in the spinal cord. So then they decided to take a cat and they said, well, maybe it's coming from the brain. So they disconnected essentially the brain from the spinal cord. And they said, well, it's not doing it now. And then they essentially trimmed the spinal cord like a log of a tree. They took off every single dorsal root ganglion. Well, what happens when you do that? You take away all sensory input. Okay, so motor input could work, but sensory input was just absent completely. And what do you know? You still get this alteration and a pattern. So it's da 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 da, off for a while, and then it comes back. Okay, and it alternates based on legs. So they thought, well, that's odd. So on the third one, what they did was they disconnected the brain from the spine, and they also, instead of cutting off the dorsal root ganglions, they kept those connected so sensory information could possibly come in, but they paralyzed it again. Okay, so this time, instead of trying to essentially do the same thing that they did in part A, but without connection to the brain, they thought, what if we squeeze the paw which will give us a stimulus. Will that change what is happening in the central pattern generator? And it turns out it does. If you look down here, there is a constant or a tonic level of action potentials as opposed to the phasic or phases of action potentials here and then like nothing. Okay, so you get action potentials the whole time during the paw squeezing. So you see all of these things and you start thinking about it because this is your field and this is what you're an expert in, and you say, well, what is a potential mechanism that could explain this? And you come up with this. Okay, so this is a possible CPG circuit. This is not guaranteed, and honestly, it's likely much more complicated. And so this is known as the half-center model, and I actually think that drawing it out can be really helpful for explaining how it works. So that is what I'm going to do right now. Okay, so what I will do is I'm going to start by drawing a line, and both of these mean, wow, that is a truly terrible line. Both of these mean neurons that are coming in from the brain, okay? And they're four different things. One is a flexor, and one is an extensor, okay? So let's call this one the flexor. Let's call this one the extensor. So imagine I'm trying to walk, okay? This would be the hamstring muscle, and this would be the quadriceps, for sake of understanding. So if you look at the graph, you notice these action potentials that are equally spaced for both things. And you say, well, that's just saying the same thing. And it is. All it's doing is it's telling the central pattern generator, hey, we want to walk. And it doesn't have to describe to the central pattern generator how to walk, because that's what the central pattern generator's job is. So it's like if management was to tell someone in the tech world a job they wanted to do, they don't have to explain exactly how to do it, because that is that person's job. They just say, hey, we want you to design this thing. Okay? So what you do is you have this come in and it binds to a neuron, and this neuron goes down, and eventually it will connect to a muscle. There may be another neuron before that or whatever, but the goal is that is trying to get to muscle, okay? These are both excitatory. Okay, now, what would happen if we just left it like this is that the flexor and the extensor would both be contracting, and your legs would just be extremely tightened on both sides, and that is not a remotely good way to try to walk. So you need a more complex system. So what happens is this actually has two branches, one that goes to the muscle and one that breaks off and comes to an inhibitory interneuron. Okay, so I just called this an inhibitory interneuron. What sign should be here? Okay, this one's positive. What should be here? Should it be a negative because of the inhibitory interneuron, or a positive because of this one? The answer is that it's positive, okay? Because it's coming from this excitatory neuron. That is where the neurotransmitter is leaving from. Now, this inhibitory interneuron is now activated, and so it's going to come down here and actually inhibit the opposite one. Okay, so when this one is on, this one is off. Perfect, right? So now I can flex my leg. The extensor is inhibited while the flexor is activated, so I can pull my leg up. Now, the problem is I would just always have my leg up, and that is, again, not great. So what you can do is you have this circle back around to itself, okay? And it inhibits itself. So what it's doing is it's inhibiting an inhibitor, okay? So let me walk you through it. So I come in with the flexor, I activate this, it goes here and it activates the flexor muscle. It also comes down here and activates the inhibitor interneuron. That goes and deactivates this. So this is contracting and this is not contracting. But after a little bit of time, it gets back to itself and it turns itself off. Now, when it turns itself off, that allows this one, which is still receiving this input, to come back on. So when the excitatory input from the motor neuron for the extensor side comes on, it also breaks off and goes to its own interneuron that is inhibitory. And again, this should be a plus to match the one that is here. And this inhibitory interneuron does the exact same thing. So it goes and it inhibits the flexor. And then it comes back around and it can turn itself back off after a little bit of time. So what you get is that when this one is on, it turns this on, and it comes in here and turns this one off for a short period of time. So whenever this one is on, this one is off. And whenever this one is on, this one is off. And so you get a few on here, and then this one is off. And then this one comes on with this one off. And it goes back and forth. And that is how you can move your knee back and forth as you walk. So this is the pattern generator that it's making, okay? So it's central, that it's in the spine, okay? It's a pattern because these are patterns, alternating patterns. And it's a generator because it's literally making it. It's taking this input that matches this one and making them alternate like this so that we can walk in a way that would make sense. Now, if you're doing diagrams like the one I just showed, one really helpful thing that you can do is to do a little bit of math, okay? So every time you see a plus, think of that as equaling a +1, okay? This works the same for the stretch reflex as well. And every time you see a minus, think of that as being a -1, okay? So when you do some of this thinking, you can essentially multiply your way to your answer. So if I'm here and I've got a plus and a plus, +1 multiplied by +1 is positive. So this is going to be excitatory right here. Now, if I come in here and I initiate this one, +1 +1, so positive. If I go this way, it goes positive, positive, negative, positive. So when you use that pathway, this one's positive and this one's negative. Now, over time, what happens is it goes positive, positive, negative. So maybe a second or two later, right? Because it takes a little bit of time to get around this loop. Negative, negative, positive. Well, when you do that, it's positive. It ends up being positive. So it is inhibiting the inhibitor, which allows you to activate this, okay? When you activate this, which is the same thing as this, it comes back up and you get the negative here, which you cannot see because I accidentally drew a positive to show this one. So you have the positive coming in here and then the negative here, so you're inhibiting this side. That could have been confusing, and so what you need to do is you need to practice diagramming both the withdrawal and the stretch reflex, and then just walk through one of the pathways and do the math that I've just described and convince yourself that it works. Okay, this is a really good way to check and make sure that you drew things correctly. Okay, so what can this information tell us? Well, if you look here, it actually shows you a bit of information. So here, if you look at the walk of a horse, the black is where their feet are on the ground, the white is where they are raised. So here, you can see there's alternation from the central pattern generator. Okay. On the trot, you do 2 and 2. Okay, so 2 up, like that, and that's what's shown here. On a pace, you do 2 up again, but it's a different 2. Okay, again, central pattern generator. And then at a full gallop, it alternates quite rapidly, and you actually have some points that are all off the ground. And you can see that there, where all 4 legs are off the ground at one point. Now, that is what we have been shown in Sherrington's work. Okay, both Dr. Mildrum and Dr. Chandler talked about Sherrington. So I would highly, highly expect to see questions about that on the exam. What you need to be able to do, in case it's a short answer, is you need to be able to describe the experiment and then say maybe why that was important. What did we find out from finding out that a horse can have all 4 of its feet off the ground at the same time? Okay. So, lastly, I want to talk about this. Some of you may have seen this in lecture and had a little bit of a panic attack, and so I want to kind of describe how it works. It's not nearly as complicated as it looks initially, I promise. And so just kind of hear me out, and I think I can walk you through it. But in order to explain this, I actually have to go back a slide to here. And essentially what happened was they wanted to see if a specific motor neuron would help you move a specific direction. So if I move from here to here, does that activate a specific motor neuron? As opposed to if I moved here to here, would that motor neuron still be activated? Okay. So what they did was they trained a monkey to move in certain directions. They said, okay, monkey, you need to be able to consistently go to 180 or consistently go to 90 or 270 or 0 or whatever, okay? And here are the results. So over all of this data, they've recorded just one neuron. That same neuron for everything, okay? And they did 5 separate trials for each direction. So this one neuron ended up getting measured like 40 different times, okay? So what you see here are action potentials. That's what each one of these dashes are. And this is where the movement begins. So this would be where the monkey would start to move towards that direction. So in this case, it'd be 90. Okay, so from its start point, it moved towards the 90, which you can see here. So it would have started to move there to touch that. So when that happened, this is where that movement began. And then you have a full second on either side of it. Okay? So if you look here at the 180, you see that this is where movement was. So a little bit before movement and during movement, you have activation of that motor neuron. You have a lot of action potentials. So this would indicate that when you move towards the 180 direction, that motor neuron is sending signals to the muscles to initiate that movement. And you see that for a lot of areas here. You see that for all 4 of these, okay? And a little bit for this bottom one. But if you come over to the opposite side and you go to 0, for example, you can see there's actually inhibition. There is nothing here. There are no action potentials during movement. So if you go from here towards the 0 direction, this motor neuron doesn't do anything, which is exactly what you would expect. You would expect that if it helps you move this way, you don't want it to activate when you're moving this way because it would hurt things, right? It's going to make it harder to move towards the 0 direction. So what you see here is that the motor neuron will help you move in a general direction. And then obviously that same motor neuron cannot help you move in every direction. Okay, so what it's showing is a motor neuron will help you move in a direction. And then you would have a different motor neuron to move in other directions. Now, what is this graph about? This graph is just showing you this data. So if you look at the direction of movement, which is 0 here, that would be this data. Okay, you see that you have very few impulses per second. That would make sense because you have inhibition here. There isn't a lot. Now, if you go to 180, that's quite high. That's about 50 impulses per second. And if you look here, there are way more impulses over that span of time. So that makes perfect sense. That is why you would have an increase here. And then if you go to 270, that's higher than 0, but much lower than 180. So let's find 270. That's down here. And if you look at it, it's pretty evenly spaced. And that's kind of what you would expect here because it's kind of in between the 0 and the 180. So this graph is simply showing you this data. So that is the majority of the material for the or of the difficult material for the Chandler lectures. But make sure you read Thursday's material because even though we did not present it in class due to cancellation, you still have to know that information for the exam. So please study that and read the notes underneath the PowerPoints. So before we go, I do have one thing I want to show you. Have you guys seen this video?
That's tomorrow, and that is it for us today. Okay, I don't know. Whatever it is, it's not right on the teleprompter. I don't know what that is. I've never seen that.
No, there is. We are going to do Sting, yeah.
Okay, but
Okay.
yeah, I can't read it. There's no words on it.
Okay. Ready? Sure.
There's no words there. To play us out. What does that mean? To play us out.
Sting is going to do, it's a video, Sting video.
What is...
For credits.
I don't know what that means, to play us out. What does that mean? To end the show?
Yeah. Yeah.
All right, go.
In 5, 4, 3.
That's tomorrow, and that is it.
Okay. In 5, 4, 3.
That's tomorrow, and that is it for us today. And we will leave you with a... I can't do it.
Okay.
We'll do it live.
Okay. No.
We'll do it live. Fuck it. Do it live. I'll write it, and we'll do it live.
Right.
Fucking thing sucks.
In 5, 4, 3.
That's tomorrow, and that is it for us today. I'm Bill O'Reilly. Thanks again for watching. We'll leave you with Sting and a cut off his new album. Take it away.
Just a castaway, but I am lost at sea. Another lonely day, where no one here for
Thanks, guys. I will see you around next time.